right, let's go and visit Fezzik. He's really a terrific fellow. Excellent with rhyming, not just big strong character. It's interesting too, right? We have Napoleon and Fezzik. Andre the Giant, great products of France. Well done, France. Terrific work. Okay, so we're going to, right, so look at this big crazy beast of a thing. I'm just going to throw some things around. It's this and this. Yeah. Okay, so this is a beast. Now we have, let's get our bases out because it sort of builds the whole story, right? So everything's been done here, although we haven't quite got. So what's the rank? All right. So again, so pivot, free, pivot, free, and it's a good sort of juicy example. And we see over here again we get pivot, free, pivot, pivot, free, right? So 2. Rank is 2. Good, and it pops out in both of those things. We had to stretch our brains to see that row reduction of A and row reduction of A transpose would end up with the same number of non-zero rows. But that's something we figured out. It's still kind of magical. You have to get your brain to think about that. All right, column space of A. Let's go for bases. Well, your bases belong to us, so we have. We go to the row reduction of the transpose, right? So it's very good. So let's put some nice brackets: 1, 0, 2, and then 0, 0, 1, 0, 1, 1. Right. So it's a 2-dimensional thing, and this is r equals 2 is the dimension. Good. Right. Dimension equals this. Let's get the row space. So we need 2 vectors here as well, but we're in a 4-dimensional space, which is horrifying. 1, 2, 0, minus 1, and 0, 0, 1, 2. 0, 0, 1, 2. Now again, these are not, kind of put them in one big box, too much. And then 0, 0, 1, 2. And this is dimension in general, n minus r, which in this case is 4 minus 2 equals 2. Good. So that's this bit. So let's tidy this up. Whoops. Okay. So there's some of our bases, and then we have the null space, the left null space. Right. Okay. So let's jump a little bit. Yes. So the dimension of column space is 2, row space is 2, left null space is n minus r, which is 3 minus 2 is 1. And in this case, we've had this from before, 2 minus 1 minus 1. Let's write like that. That's not right. 2, sorry, plus 1. Let's do that one. Yep, and then a minus 1 here. And yeah, for the left and for the normal null space, minus 2, 1, 0, 0 is one basis vector. Again, this is from before. 1, 0, minus 2, 1. Yep. Okay, so 4-dimensional space mapping off into, so this is just a horrible thing, right? So this is a horrible beast of a thing. So let's try it. So there's a plane somehow that has these 2 vectors in it. 1, 2, 0, minus 1, and 0, 0, 1, 2. This is row space. And this is all good. This gets sent, all of this plane gets sent over to a plane. Let's draw it like this, just making up. we'll have a nice, we'll have these vectors in here, 1, 0, 2, and 0, 1, 1. They're not at right angles to each other. Let's just imagine they're here. They are at right angles to this character, 2, 1, minus 1. Right, so here's left null space. So we can't make anything along this line. Yep. But we can make everything in this plane, right? So if you have a vector that has some part that's not in this plane, we have to subtract off the part that's in the left null space direction. All right, so this is a three-dimensional space over here. So this is R3 M. This is R4 eek. And so there's a plane, this plane, right? So A times XR equals B maps 2D plane in R4 to 2D plane in R3. So we'll take it, and we saw this before. We had lines that were being stretched, right? Now it's gonna be stretched in particular. It could be stretched differently in different directions, right? So you imagine you take this big plane, put it over here, and you go stretch a little bit. All right, and so, and all, you know, and part of this is all this, there's a rotation that's being encoded somehow, and of course putting it into another dimension. And then, weirdly, there's another plane here. Because it's 4 dimensions, we can't do it. So properly -2, 1, 0, 0, and 1, 0, -2, 1. So these two vectors are at right angles to these two vectors. So there's lots of little things in this direction. Everything in this plane gets sent to 0. A times x null equals 0. But it's again, it's the same story. I've lost my picture. Where's my picture? Is it underneath? Nope. Yeah. And so that's why we lift away from these things to this more abstract picture. So in general, this could be, you know, very high dimensional. We know how they match up in terms of, you know, exactly what the dimensions are in terms of M and N and R, but they could be very big spaces, and that's impossible for us to understand. But this is about as scary a thing as I want to try to draw. Okay, so there are 3 big examples, right? So we went through the simple 2x2 one, and we were able to get everything out. We call this one, this little character here. This is Wesley. We're able to get everything out, and I'll photocopy all these things. Hilarious. Scan all these things, you know, and solve it, and really show the picture very clearly. This is it. Fine. It gets more complicated when we move up to just a 2x3. Just a 2x3 gives us, you know, this nasty looking thing here. It's a plane, a line, but again, ultimately, you start to see that there is some internal part of each space that gets sent back and forth in a clean way. And so if you can go back from that B to that X, and you can go from this X to this B, there's a unique mapping between them. It's a one-to-one mapping. And then we start to get into some horrors with this Fezzik character. All right, so